Good morning, everyone. We have a warm-up here for you to try. Hit pause, and then when you're ready, press play for the answers. All right, now you have had a chance to do the problem. Notice we are given the actual derivative this time, and it's written in factored form. That's very convenient and very friendly when we are asked to find and classify the critical points of y. So let's actually analyze this. What do they mean by critical points? Remember, critical points are whenever the derivative is equal to 0. Well, what I need to do is I need to take this derivative and set it equal to 0. Since it's already written in factor form, we will take each parentheses, set it equal to 0, and solve. First one is solved for us. Second one is very easily solved. Third one, I actually have to take the square root of both sides first, which is friendly, and then subtract 3. So I have 3 critical points. Now our job is to actually classify them. So I'm going to create a sign chart. So remember, the sign chart is just a number line that analyzes what's happening to the left and right of each of the critical points. So I have to write it in order, -3, 0, and 4. And we're going to test the sign value. Now normally I would say look at the graph of the derivative to identify where we're increasing, decreasing. But this case it's a little harder. I'd have to FOIL, and I still might not know what the x to the 4th graph would look like. So what if we just test points? Let's pick a point to the left of -3. Let's test -4. Now again, keep in mind I'm only looking for the sign value, so I don't care what the actual number is. But what if I plug -4 in here? If I plug -4 in for x, I get a negative output. If I plug -4 in here for x, I get -8, which is a negative output. And notice, x plus 3 squared. I don't care what this is. Whatever value we have squared will always be positive. So I'm going to leave this one. This is always positive, which means these two factors determine the sign of our derivative. So a negative times a negative ends up being a positive at 4. Now let's test the value between -3 and 0. Let's try -1. And again, I'm only looking for the sign. Right? So if I plug -1 into x, I get a -1 back. If I plug -1 into this factor, I get a negative output. And a negative times a positive, remember this is always positive, will result in positive derivatives. All right. So then I have to pick a value between 0 and 4. Let's pick +1. And let's check the sign values. Plugging +1 in here produces a positive output. +1 for this factor produces a negative output. And this is always positive. So a positive times a negative times a positive will always be a negative output. And then let's check any number past 4. We could pick 5, 6, 7. We could pick infinity. Let's pick 5 for simplicity's sake. So plug in 5. I end up with a positive output. 5 minus 4 is a positive output. So a positive times a positive times a positive is a positive. So there's my sign chart. That actually helps me analyze what's going on to the original function. So let's think about this. At x equals -3, we have positive slopes. And then I have a 0 slope. Remember, any of these critical points were 0 slopes. So I go from positive slope to a 0 slope. And then I go right back to positive slopes, which tells me there's a flat spot right there at -3. Right? We go from increasing, we flatten out, and we increase again. At 0, I go from positive slopes to a 0 slope, and then I go right to negative slopes. So I go from increasing to 0 to decreasing. There's a maximum at 0. At +4, we go from negative slopes to a 0 slope to a positive slope. So we have a maximum value. Now, remember, none of this would give you credit. You would get 0 credit if you put this on a test or a quiz or the AP test. So what do you have to do? You actually have to justify your logic in a written sentence. There is neither a max nor a min at -3 because y prime does not change signs. So I'm justifying that there's a flat spot, or saying no max, no min. At x equals 0, there's a max value at x equals 0 because y prime changes signs from positive to negative there. And then there is a minimum value at x equals 4 because y prime changes signs from negative to positive there. So this is the work we're looking for. That's the justification. Remember, a sign chart only helps you organize your thoughts. All right, now let's look at why a sign chart might be helpful. I could also ask you to identify intervals where y is increasing and decreasing. Let's think about what that means. If the function y is increasing, we know that its derivative has to be greater than 0. And for decreasing, we know that its derivative has to be less than 0. Well, the sign chart already tells us the intervals where we're increasing and decreasing, so we can write those down. All right, notice my justification here. I'm saying the function y is increasing on the interval from -infinity to -3. And then we have a little 0 spot there, so we don't write actually at -3. Then we're increasing from -3 to 0. Since the derivative is greater than 0, that's what clues us in on the fact we're increasing. Y is decreasing on the interval from 0 to 4, since y prime is negative, less than 0. So we just used the first derivative test to determine where maximums and minimum values occur, and we related it back to what was happening at the derivative. So we're going to use this again. This is what we learned on Friday. We'll show you how to do it more analytically today. If you need to press pause to review this, you can. But let's start off with this example here. And it says, suppose h is equal to the function 4x to the third minus 6x squared plus 1. Find the local extremas of h. So this is where we're going to do the first derivative test. So take the derivative, set it equal to 0, make a sign chart. Go ahead and hit pause and work through that, just like we did in the warm-up. First step, take the derivative. The derivative is 12x squared minus 12x. Then we have to set the derivative equal to 0. Notice how I factored in that same step. I said both terms have a 12x in common, so I pulled out a 12x. And then I set each factor equal to its own 0 and solved to find my critical points. Now we're going to create the sign chart just to help us visualize what's going on, and then we can make our conclusions about the extrema. So we're going to do that same thing. Notice how I have my derivative in factor form right here. A lot of times it's a really quick, friendly way to determine what's going on with the derivative. I'll show you another way after that as well, but picture if I plug in a value like -1. So I'm going to test -1, it's to the left of 0. If I plug in -1 to the first factor, I'll get a negative. If I plug in -1 to the second factor, I get another negative. A negative times a negative is a positive. So then we're going to test a value between 0 and 1. So picture plugging in 0.5. And again, the only thing I'm focusing on is the sign value. If I plug in 1/2 times 12 will be a positive value. 1/2 minus 1 is a negative, so a positive times a negative is a negative. And then I need to pick another value to the right of 1. We could pick any number. I'll pick 2. So 2 times 12 is a positive. 2 minus 1 is a positive, and a positive times a positive gives me a positive sign value. All right, so that's how we can determine our sign chart. Another way to think of this, and sometimes it's friendly, is look at the actual derivative equation. Notice how it's a parabola opening upward. If I was to draw the parabola on a graph, it would go through 0, it would come down, and then it would go back up to 1. Well, look at that. Here, the derivative's above the x-axis, that's why we're positive. Here, the derivative's below the x-axis, that's why my signs are negative. And then here, we're above the x-axis, so I have positive signs. However you want to think of it. But now we can make our conclusions based off of what kind of extrema do we have at each spot. So if I look at my slopes to the left of 0, my slopes are positive, so the function is increasing. And then to the right of 0, they're decreasing. So I'm going up and then down, which would tell me I have a maximum at 0. At x equals 1, I have negative slopes, and then I go to positive slopes. So I go from decreasing to increasing, which is a minimum. Now remember, sign chart is not our answer. We have to justify that, so write out our solutions. Pay special attention to the way that we write our answer. So I know that there's going to be a maximum at 0, but what is the maximum? What happens when I plug 0 back into the function, the original function? Notice I end up with 1 as an output. So here's my justification and the way that I'm going to earn credit for this type of problem. There is a local maximum value of 1 at x equals 0, because when I plug 0 back in, 1 comes out. So that's the maximum value of 1, and it's occurring at 0. Now the reason why I know that is the first derivative test. It's because the function h prime is changing signs from positive to negative at that value. So what if I plug 1 in? If I plug 1 in here, I end up with 4 minus 6 plus 1. So I can make my conclusion. There is a local minimum value of negative 1 occurring at x equals 1. So when I plug in 1, I got negative 1 as an output. That is the actual minimum value, and it occurs at 1. We know this because h prime changes signs from negative to positive there. Okay. Now we want to answer the question, when is h concave up and concave down? So to solve this problem, if you know it, go ahead and try it. If not, you might want to take a look back in your notes. But go ahead and hit pause and try this. Okay, so now what do we know about concave up? Well, we know the second derivative has to be greater than 0. For concave up, concave down, we know the second derivative is less than 0. So that's all based off of the second derivative, which means I now have to take the derivative of the original derivative. So the derivative of 12x squared is 24x. The derivative of minus 12x is minus 12. And then we want to find the spot that makes that equal to 0. So set the second derivative equal to 0. Notice if I add 12 and then divide by 24, I get 12 over 24, which is 1/2. And then what we're going to do here is we're now going to make another sign chart, but this time we're going to make a sign chart for the second derivative. So I know that it has a potential point of inflection at 1/2. I need to test the values to the left and the right of that. So if I want to test a point, a very friendly point to the left of 1/2 is 0. If I plug 0 into the original function, notice I get negative 12 coming out. So the second derivative will be negative to the left of 1/2. To the right of 1/2, let's pick another friendly number, 1. If I plug 1 in here, I end up with 24 minus 12, which is a positive. Now you could also say this graph is just a linear function that's going to look like this. The graph of the second derivative is a linear function, so notice its outputs for the second derivative are going to be negative to the left of 1/2 and positive to the right of 1/2. So it's two ways to analyze that. But now we can make our justification based off of what we have here. I know when I'm concave up, I have positive second derivatives. Concave down when I have negative second derivative. So we'll make our justification the same way we did up top. So to justify, we know h will be concave up on the interval from 1/2 to infinity, because that's where h double prime is greater than 0. And we know that h will be concave down on the interval from negative infinity to 1/2, because the second derivative is negative. I always kind of like to erase these so we don't get screwed up. Those were our test points. Notice how I'm always making reference to the original function. So we always relate back to h. Part 3 says find any points of inflection for h. Well, points of inflections are where we change from concave up to concave down, or vice versa. And notice our sign chart can actually kind of help us determine that. Here I changed from going concave down to concave up. So that proves that at x equals 1/2, there's a point of inflection. The only thing we have to do is to find the point. This should be, we didn't know at the time if there was 1 or more or 0, but in this case we actually have 1. Notice it says point. So a point refers to an xy pairing, so I'm going to actually have to take 1/2 and plug it back into the original function to find the output. So I'll do that here in a second. So we have to figure out that what is the output when x is equal to 1/2. So I'm going to take and find h of 1/2, plug 1/2 in, simplify. When you do, you're going to get 0. So then how do I justify this actual answer? H will have a point of inflection at 1/2, 0 because there's a sign change in h double prime there. I don't really have to say that it goes from negative to positive because it can go from concave down to concave up or concave up to concave down, and it will still give us proof that there is a point of inflection. All right, the last problem for today, the last piece, is we're going to confirm question number 1. We're going to confirm the local extrema, but this time we're going to use the second derivative test. So remember, the first derivative test was all using the first derivative and the sign change. What we're going to do is do a quick review of what is the second derivative test. So this is just a quick recap from Friday as well. Just remember, if C is the critical points, which keep in mind we know our 2 critical points, then remember we know that the derivative is equal to 0, so that's where horizontal tangents occur, which also means maximums or minimums occur at those points, potentially. So if the second derivative is negative at one of those critical points, that tells us there's a local maximum there. Remember, that's concave down. If we're concave down and we have a horizontal tangent, then it has to be a maximum. If the second derivative is positive at a critical point, that means we're concave up. Then we have to have a local maximum. If the second derivative is equal to 0 or does not exist, then C could be anything and we don't really know. So let's use this second derivative test to actually confirm. What do I need? I need the critical points, so 0 and 1. We already found those. And then I need the second derivative. So x equals 0, x equals 1. And what we're going to do is we're going to test those into the second derivative. So I want to find what is the value of h double prime of 0. So go back up to the second derivative. Now we're going to plug in 0. So notice my answer is negative 12. I'm more concerned with the sign value. Notice negative 12 is less than 0. So that means that at this point, the second derivative is negative, which is concave down. If it's concave down right at 0, then that must mean that there's a maximum point at 0. Again, none of this isn't really true justification. We have to write it out in words. We'll do that in a second. But let's test the other point. Let's test 1. If I plug 1 into the second derivative, I get 24 minus 12, which is a positive 12. Notice positive 12 is greater than 0, so that means that the second derivative is concave up right at the critical value of 1, so that means that at that point there must be a minimum. So how do we write our answer? So here's my answer with justification. We know by the second derivative test there is a local maximum at the maximum of 1 at 0. Now, we know that the second derivative is negative there, so that's going to refer to concave down. So therefore there has to be a maximum value. And then remember, where did the 1 come from? I took the 0 and plugged it back into the original function to find its output. But this is your justification that you need. So likewise, there's a local minimum at x equals 1 because the second derivative at x equals 1 is positive, which is concave up, so therefore low value. And then anytime you got to find the outputs, you just plug in x into your original function and you'll get the actual outputs. So that's the second derivative test. Kind of a quick way, if you already know your critical points, to test if there's max and mins. Focus on the justifying. Your homework should look like this. Every single homework problem tonight should have a sentence written out with the answer plus the justification. All right, homework tonight is through the textbook. Good luck.